All right, good morning. Okay, so today will be the 5th lecture. We'll talk about convolutional neural networks. So just to make a recap of where we are currently in the course. So we are basically done with the basics of deep learning. So we have covered together the recipe to build a simple neural network, which we call multi-layer perceptrons, and which we have built starting from a primitive unit, which, if you remember, is the logistic regression unit, which we have composed in parallel to produce layers, and then in series to produce these so-called multi-layer perceptrons. Then we have seen that in order to train this neural network, so to find good combinations, good values of the parameters, we need several components. So first we need to define a loss, which is basically the criterion that we use to quantify the quality of the predictions of the neural network. Then we said that we would be using numerical optimization algorithms like variations of stochastic gradient descent to optimize these parameters. And so this was the topic of last week, where we have seen a few optimizers which are used in deep learning, and Adam is the main one of them. But the ingredient that we need in this numerical optimization algorithm is the gradient of the loss with respect to the neural network parameters, and we've seen automatic differentiation algorithms to do that. Okay, so basically all this part is now covered. So basically you should, and this will not change in the next lectures. So we'll still be instantiating neural networks. We'll still be training them using the same optimization algorithms, and we'll still compute the gradients exactly in the same way. Okay. So what we'll cover now in the second half of the course are just architectures of neural networks that you can use for specific tasks. And today and next week, we'll cover neural networks that are specifically tailored for images. So today we'll talk about convolutional neural networks, meaning that we'll be then able to use this neural network, for example, to solve tasks where the input is an image, like if you want to classify images or if you want to do regression on images and other things like this. And then next week, we'll consider more advanced architecture to solve more advanced computer vision tasks, like detecting objects, so locating objects in an image, detecting or segmenting an image, which is about classifying the pixels, the individual pixels of an image, and so on and so forth. Okay? Okay, so basically the main question we'll try to answer today is how could we make, in a sense, neural network to see? Okay? We'll basically see two new kinds of layers, two new kinds of primitives. The first one is the convolution, and specifically the convolutional layers. And the second is the pooling mechanism. And if we combine the two of them together with what we have seen before, so regular fully connected layers and nonlinear activation functions, then we'll, from all these primitives, we'll build convolutional neural networks. Okay? All right. So I don't know if any of you know, how do we actually see? So what do you know yourself about the biology of vision? Okay, you use light to see. Okay. So there is light which arrives to your eyes, and then what? Yeah. Okay. Yeah. So we have a retina, which is like a sensor for light. And the neuron, okay, or many of them actually. But do you have any clue about what's going on, or beyond that? Yeah. Okay. Okay, and these neurons, where are they? Okay, but that's fine. So this is something which has been studied since the 50s, 60s, and the main scientists behind these discoveries are David Hubel and Thorsten Wiesel, and basically they have identified the neural basis of how the information is processed in the brain to give rise to vision. And they were awarded the Nobel Prize of Medicine a few decades later for that discovery. And so I want to spend a few minutes on that because what we'll see in terms of neural networks will be quite strongly inspired by what we know actually from the visual perception system in humans and animals. All right, so so basically what they did was to do first experiments on living animals, and specifically on a cat, to which they put electrodes to basically record the electrical activity of some regions or some regions of the brain or some neurons if they have very precise sensors. Okay, and what they've discovered is that indeed, as you said, they are neurons responsible for detecting patterns. Some neurons will detect lines in some orientations, for example, vertical lines or horizontal lines. Some others, so you will have, for example, neurons for detecting vertical lines and others for detecting horizontal lines or diagonals. Some of them also will be detecting motions. So I will just first let you watch this video, which is about the story, and then we'll watch a second video about basically the model, the physiological model that they considered as a plausible explanation of what they were observing during their experiments.
The researchers actually listened in to individual nerve cells firing in the anesthetized cat as they presented it with different visual images.
When we started working, Torsten and I, in the late 50s, we set up our first experiments, and they didn't go well because at the beginning we couldn't make the cells fire at all. We'd shine lights all over the screen, and nothing seemed to work. And rather by accident, one day, we were shining small spots, either white spots or black spots, onto the screen, and we found that the black dot seemed to be working in a way that at first we couldn't understand until we found that it was the process of slipping the piece of glass into the projector, which swept a line, a very faint, precise, narrow line across the retina. And every time we did that, we'd get a response.
Okay, so now that you have a bit more of an understanding, the experiment that they did in more details was to take this poor cat and then put electrodes a bit everywhere, but close to the eyes, okay, because they wanted to record the electrical activity of the neurons close to the retina, okay? And so they were, in a sense, listening or recording this electrical activity, and they were also stimulating the cat by showing it shapes. For example, you saw in the video this black shape, this black dot. But what is interesting is that they discovered that actually these shapes, this black dot shape, does not lead to any interesting electrical activity. They don't record anything when you show this black shape, this black dot shape to the cat. But what they discovered instead by accident, actually, is when they were, so they were using this, how do you call that in English? Retroprojector or something like this, you know. So where you have a piece, a transparent piece of plastic, okay, on which there is this black dot, okay. But if you paid attention at the video,
Found that it was the process of and we found that the black dot seemed to be working in.
okay, so you hear this sound. This sound is just the electrical activity, okay, in sound. And what happens is that you hear this sound when the border of the piece of glass is within the receptive field of the cat. Okay, so you see this line, very faint line, and it's only
that at first we couldn't understand until we found that it
when
was
there
the
is this
process of
line that you
slipping
hear
the
these
piece of
measurements.
glass into the projector, which swept a line, a very faint percent.
Okay, so basically from there, their hypothesis was to say, okay, these neurons or these regions that they are from which they are making these measurements, supposedly they are just trying to detect lines, and these lines in some orientation. Okay, but that's something actually they discovered by accident. But then they quickly understood that this was really the key. And from there on, then they make further experiments to see if indeed we had neurons responsible for detecting lines in one or the other orientation. Also, if we have neurons that are only responsible for specific regions in the receptive field of the cat. Okay, so you have neurons that basically always look at the same position within the receptive field, and others that are targeting other parts of the receptive field. So let's watch this video together.
In this classic experiment by David Hubel and Torsten Wiesel, a microelectrode is implanted in the primary visual cortex, or V1, of an anesthetized cat to record the receptive field of a single neuron. A bar of light is shined on various locations in the cat's visual field. The microelectrode is connected to a speaker so that each action potential is registered as a clicking sound. The neuron fires vigorously to the onset of a bar of light at about 45 degrees. This firing pattern of the neuron is recorded by drawing X's along the bar's location. This is the on receptive field. In addition to the on receptive field, the neuron also responds to changes of light on the parallel space on either side of the X's. In this case, we hear clicking sounds when the light is turned off. These are the off fields of the neuron and are recorded as triangles. The neuron responds with more activity to the area below the X's, marked with 5 triangles, than the area above, marked with 3 triangles. Each individual neuron has its own preferred orientation and region of the visual field to which it responds. In this cell's receptive field, lines of triangles, referred to as the off-surround regions, flank the X's, which are the on-center region. The firing rate reaches a maximum only when the light is shined on the X's at the preferred orientation. Cells of the primary visual cortex with this type of receptive field and orientation preference are called simple cells. Widening the bar of light causes the firing rate to decrease. Diffuse light produces no response in the neuron, despite the fact that it shines upon the on-center region marked by the X's. Observe that the neuron fires when the edge of the light moves, leaving a portion of the triangles in darkness. Compare this again to the diffuse light. In this experiment, the same methods are employed to measure the receptive field of a different neuron in V1. Different orientations are tested until one is found that triggers maximum neuronal excitation, indicated by the intensity of the clicks. This time, a solid line is drawn to record the area of maximal firing. The cell measured in this experiment is called a complex cell. Compared to simple cells, a complex cell has a wider receptive field, and it fires when a bar of light is shined on any part of the receptive field. Like simple cells, complex cells are highly orientation selective. As indicated by the clicks, the further the orientation strays from the preferred angle, the less the cell exhibits an excitatory response. Complex cells respond to either light bars on a dark background or dark bars on a light background. Thus, complex cells can be considered more abstract line edge detectors than simple cells. They respond to the line edge on or off anywhere in the receptive field, as long as they are in a particular orientation. Hubel and Wiesel proposed that the receptive field of a simple cell can arise from the convergent input of a series of LGN neurons. The circular receptive fields of the LGN neurons, represented by the concentric circles, combine to form the receptive field of the simple cell. The on centers of LGN neurons, represented by smaller circles filled with triangles, combine to form the on center of the simple cell, as indicated by the rectangular dashes. Likewise, the receptive field of a complex cell may depend upon the input of simple cells earlier in the visual processing pathway. Here, the dashes represent the receptive field of the complex cell, which is created by the convergent input of the receptive fields of multiple simple cells that have the same orientation preference. This feed-forward model, where a receptive field of a neuron is shaped primarily by neurons at an earlier visual processing stage, is a logical inference from the experiments just viewed. But the feed-forward model, as compelling as it may be, has yet to be definitively proven through experiments.
Okay.
Viewed. But the feed...
Okay, so just to summarize what we've seen, so what they've discovered is that if this is the, let's say, the entire field of view of your eye or of the eye of this cat, okay, then they discover that there are at least two types of cells, okay, one which they call the simple cells, this one that you see there in light green, and the simple cells, they will be basically they will trigger, so they will be very reactive if there is, for example, a line at some position, okay, at some orientation. So in their experiment, so if you, for example, you have this cell like this, okay, and this cell is itself connected to these other neurons that they were talking about, which are defining this. And so they recorded the electrical activity if there was this line at this orientation, at this precise location. You could listen that if they were rotating the line, the electrical activity was disappearing. Okay? If instead you have a line like this, then this neuron does not fire. Okay? If you have another line but at another position, since this neuron is not connected to this other part of the field of view, then it's not producing any electrical activity either. Okay? So basically you have these simple cells that which you can abstractly consider as feature detector, which are location specific. Okay? You have this cell, this one, which will be trying to detect if at this position and only at this position there is a line, for example, an oblique line. Okay? You may have other simple cells that are also, in a sense, watching this region, but looking for other patterns. Lines, for example, in other orientations. Okay? And then the model that they propose is just to say, okay, we will have several of these simple cells. Okay? for example, this one will be looking now at this region, and this other one at this region, and maybe even a fourth at this other region. But all of those will be looking for diagonal lines. Okay? And then the idea is to say these neurons are themselves connected to another neurons, which they call a complex cell. And this neuron will be excited, will fire, if one of those simpler cells fires. Okay? And so that means this one now would be also detecting, would be on, in a sense, if one of those simpler cells is on. Okay? And the effect would be that now this complex cell would be effectively looking at this entire region instead of these smaller regions. Okay? And if there is a line, a diagonal line anywhere within this region, then one of those simple cells will fire, and the consequence is that this one will also be excited. Okay? And this is what they also observed experimentally by just putting the microelectrode closer to these other cells. They could observe this behavior. Okay? So this idea is quite fundamental for today's lecture. Is this idea that you will have some kind of feature detector, and then we'll be composing this feature detector, okay? And the result for us will be what we call a convolutional layer, okay? A convolutional layer itself will be close to something like this, but when you combine this with the pooling layers, which we'll see later on, then it will be very similar to this whole model of the actual brain. Okay, now the question we'll try to answer today is, can we equip our neural networks with what we call in the field inductive biases that would be tailored for vision? Okay, so given what we know about vision, can we put this knowledge inside directly the architecture of a neural network? And the specific inductive biases that we'll be talking about today are first locality. Can we have neurons, artificial neurons now in a neural network that would be targeting a specific location? Or can we have neurons, I'm just saying the same but in a different way, can we have neurons whose activation is only computed on a local region of the input? Okay, instead of using the entire input. Can we have neurons that only use a subset of this input? Which is exactly like a simple cell, which does not use the entire image, but only a subset of that image, a subregion of that image. Can we also have a neural network that would build something like invariance to translation, meaning that if we have this line, but we translate it, we still want the neural network to respond, okay? Exactly like a complex cell would respond regardless of the location of that line, okay? So, for example, in machine learning terms, can we have a classifier, let's say, which would have to detect, for example, if there is a cat or a dog of an image, which would continue to work regardless of the location of the cat or the dog within the image. Okay? And finally, can we be inspired by this idea of combining or composing these cells together in some kind of hierarchy to build an architecture of a neural network? Okay, so that's what we'll try to do today, and we'll see it's not that difficult. Okay. But just to insist on this aspect once again, let's say we have these two images, A and C, okay? And we have a neural network that processes these images, for example, to classify them. So for that image, certainly you would like the neural network to produce a label corresponding to, I don't know, something like a mountain. And for this one, to produce another label, which would be, for example, it's a room or something like this. Okay? Now, if you look at these two other images in B and D, they are almost the same as the one above. They are just translated by or shifted by a few pixels. Okay? What we want when we say that we want the network to be invariant to translation is for the output of the neural network to be the same for these two images and to be the same for these two images. Okay? Even though one image is a translation of the other. Okay? But we want the output to remain invariant to the translation that we apply to the input image. Okay? And similarly for this other task, where it would not be about classifying the entire image, but classifying, for example, the pixels, then we want something slightly different. If we say that we want to classify every pixel, so we have a neural network that takes a raw image as input and then produce as output a mask, okay, of the same size of the input image, and at each location you have the classification that's associated to each pixel. Now, if we shift that input image, what we want is for the mask that we've produced on the original image to be the same but shifted, because it's still in a sense the same image, only shifted. Okay, so in this case, what we say is that in that case, we don't want invariance to translation, we want equivariance to translation. Meaning, if you shift input image, so if you take an input image, you produce some output, okay? Now, we say that we want equivariance to translation and we want that by construction of the neural network, such that if you shift the input image, that will also shift the output. Okay? Okay, so this is what these are things we want to try to build now in a neural network. All right. So convolutional neural networks, they are not new. The very first, I would say, instance of a neural network was proposed already in the 80s. It was called the neocognitron by Fukushima. And this architecture is directly inspired by the discoveries of these two guys, Hubel and Wiesel. So in the diagram that you see above, it's directly the diagram that Hubel and Wiesel proposed to explain the visual perception system in the cat. You recognize the retina, then these LGB cells, which were quickly mentioned in the video, and then simple and complex cells. And then, I've not elaborated on that yet, but then you have other layers or other layers in the hierarchy of the cells. You can then say that after this first composition of simple and complex cells, you have other cells, other simple cells that are now connected to these complex cells, and you would have several of them that are themselves connected to complex cells. Okay, so you can compose this mechanism in a hierarchy. And so Fukushima proposed this architecture, the neocognitron architecture, which is basically a direct computer implementation of this model. Okay? And what we'll see today is actually very close to that. Okay, what we use today, still in 2025, is very close to this architecture. However, it's only much later that we managed to train this architecture, because at the time when Fukushima proposed this architecture, we didn't have any good algorithm to train these neural networks. So together with this architecture, Fukushima proposed a biologically inspired training algorithm to update all the parameters of these architectures. But this training algorithm, unfortunately, proved to be very inefficient, so inefficient that you couldn't actually use it to train these architectures. Then, a bit later, in the 80s and 90s, Yann Lequin proposed a convolutional neural network, which he proposed to train, which was also inspired by the neocognitron by Fukushima. But the main difference is that he proposed to train this architecture simply using gradient descent, backpropagation to compute the gradients and then updating the parameters. And that worked. All right, so let's take now the pieces of a convolutional neural network one by one, and once we'll have defined all of them, we'll compose them to produce convolutional neural networks. So the first element today will be about convolutions. So a convolution mathematically is quite simple. So I will say that a convolutional layer will basically apply the same linear transformation exactly as a fully connected layer, but the main difference is that this linear transformation will be local, so only apply to some smaller region of the input. Okay? And you apply this same linear transformation locally everywhere on the input signal. So let's say, for example, you have this input vector, and we say that, okay, we want to apply only locally a small linear transformation of this region and of this region only. Okay? So the way to do that is just to take some subregion of the input, for example, 4 consecutive elements, and then to apply a linear transformation to these 4 elements. Okay? So the simplest linear transformation is just to multiply these elements by a vector of the same size. Okay? So we just do a dot product, which is represented by this green box. Okay? And what we do is that for every possible location, so every possible alignment of the input with this green box, we compute the dot product, meaning we just compute the product of the elements from the input region and the green box. We sum all these values together, that gives us a number, okay? And we report this number in some output vector. Okay? And then we repeat that for the next location. So we just slide the green box to the next possible location. So now we would be, for example, aligning the green box with 4, -1, 0, and 2. And we compute the dot product of this subvector together with this box, and that produces a value of 0. Okay? And then we iterate like this over all possible locations. So mathematically, you can define this in this way. So in the case of first one-dimensional convolution, so where we assume that we have a one-dimensional input vector, so vector of size W, then we say that this green box is what so the name that we give to this green box is a convolutional kernel, okay? And we say that this kernel is also a vector, but it's a vector now of size lowercase w, where lowercase w is smaller than the size of the input vector. Okay? So we have a big and a small vector. And then we say that the discrete convolution of the first with the second, okay, is a vector of size big W minus small w plus 1, such that each element I of this output vector, okay, is defined simply as the sum of the element-wise products of the subregion of the input vector and of the kernel elements. Okay? Do you all follow so far? Okay. So you have two examples here of two one-dimensional convolutions. So let's say we have this first vector, x, then we have this kernel, -1, 1. If we compute the convolution of this x vector with this kernel, then we produce this output vector. Okay? And so how would we be computing that? So we have 0, 0, 0, 0, 1, 2, 3, 4, and then that's it. Then we have the kernel, -1, 1, plus 1. Okay. X, u. And then we say that the convolution of x with the kernel u is a vector. Okay. the first element, so you align the kernel with the two first of size 2 with the two first element in X, and then you compute the element-wise product. So 0 times -1, 0, plus 0 times -1, 0. Then you shift the kernel by one position to the right. Again, we will have 0. Then you shift, we'll have 0. Then we have this. So here we have 0 times -1, 0, plus 1 times 1, 1. Then we shift. We'll have -1 times 1, -1, plus 1 plus 2, 2. So -1 plus 2, 1. Okay, and we continue like this. And what we have, in this case, is 1, 1, and then 0. Okay? Another example would be this one, where we start from these vectors where we have zeros everywhere, but at 3 locations we have 3, okay, which correspond to these bars. Then we compute the convolution of this kernel, of this vector with the kernel 1, 0, 1, and that would produce this output. Okay, why is this something interesting? Because actually these kernels, it's as if they were trying to detect features, to detect patterns. Okay? So for example, for this kernel, you see that you have some positive output when not everywhere, only at some location of the input. Okay? And specifically for this kernel, -1, 1, you would have a positive input when you have a gradient in the input. Okay? When you have a change of value, an increasing change of value. Okay? And you see that you have this positive input, basically when the input signal is increasing, but when it's flat, either there or there, you don't have any output. And similarly for the second example, when you compute the convolution with this kernel 1, 0, 1, it's as if you were trying to detect a pattern where you have a high value, then nothing, and then a high value. Okay? And so when you see that the output of the convolution is maximum at this position, which is exactly where you have some positive quantity, nothing, some positive quantity. Okay? Which is precisely what this kernel is capturing. And you have other non-zero values, there, and there, when the pattern is only matched partially. Okay? So for example, at this position, at the first position, you have nothing, nothing, something. So so this is not met. The first element is not met, but you have nothing and then something. Okay? Okay, we can generalize this definition of one-dimensional convolution to two-dimensional convolutions. Okay, so now we would upgrade our vector x to a matrix of size h times w. And we would upgrade the kernel u also to a matrix of size small h times small w. Okay. And then we say that the discrete convolution of x and u is now not a matrix but a vector. Okay. And each element gi of this matrix is defined by this sum of element-wise products. Okay. But it's exactly the same as before. Now we would have a matrix, X. We would have a small kernel U. Okay? And then we just, so let's say this is like this, maybe. So we consider all possible ways we can place this kernel on the input. Okay? So the very first position would be to align this one with this region. Then we compute the element-wise products. So this element together with this element, this element with this element, this element with this element, this element with this element, and then we sum everything together. And then we report in another matrix the result of the sum of element-wise products. Okay? And this is what you have there in the formula. Okay? So what intuition do you have about this formula? Why do you think that's something that makes sense and which is worth putting in a neural network? So why do you think it's a good idea to say that element gi is this double sum over all the element-wise products? Yeah. Really? The kernel elements, the U elements will not rotate. So there is no learning yet. The convolution actually is not rotation invariant. So how do you interpret this formula? That's just what I'm asking. Yeah. Keep the features you want to. What do you mean? Uh-huh. Okay. Mm-hmm. And why this formula? So you say intuitively it detects, but where do you see it detecting anything in this formula? Yeah, which is defined in this way. So okay, so let's take another example then. So let's say this is the input image. Okay? So it comes with many pixels. I will not draw everything. Okay? And then we have maybe a cat like this. Okay? And then something like this. Okay? That's your image. And then we have a kernel, maybe of size 3 by 3. And the content of this kernel may be something which looks like this. Okay? So it will be trying to detect, or at least that's what I want you to understand, to detect pointy ears. Okay? In the form of small triangles. Okay, and then I'm saying, okay, what we'll do is to apply this kernel on this image following this formula. And if you apply this formula, it should detect these pointy ears. Why is that? So what will happen is that we will be sliding this kernel everywhere on this image. So the output will be another image, more or less of the same size, a bit shorter, where we'll have also many values. These values, if there is nothing there, if it's the sky, and then we compute the sum of these element-wise products, there we'll have 0, 0, 0, 0, 0, 0. So we'll have mostly 0 everywhere. Okay. Until we arrive more or less there. And when we are there, so when we align the kernel, let's say with this position, with this region, okay, then we'll have a high value. Okay? I don't know, maybe 10 or something. And then we'll have 0, 0, 0, 0. Why is that? Well, if you look closely, this sum of element-wise product is nothing else than a dot product. If you flatten this matrix into a vector, if you flatten this smaller matrix also into a vector, you compute their dot product, you are doing effectively the same as that. Okay? Now, geometrically, how do you interpret a dot product? A dot product is a similarity measure. Okay? You will have a high dot product if this vector is aligned with this one. If they are not aligned, you will have a value closer to 0. Okay? So these convolutions, they are basically just computing similarity scores everywhere on the image. And the results will be a map like this, where you will have high values corresponding to subregions of the image that are very, very similar to that kernel. Okay? That's it. There is nothing really more to understand about that. But really, the intuition is that this convolution, it's just about detecting patterns using as a similarity measure a dot product. Okay? Okay, now we can also extend the 2D convolution to tensors, where we have a certain number of channels. So these tensors, in the case of images, will just be some kind of cubes, so a 3D input tensor, where we'll still have two spatial dimensions, the height and the width, h and w, but we'll add a third dimension, which we call the channels. Okay? So in the case of an image, we have h, w, but on a computer, an image is represented using 3 channels because we need 3 values to represent the red color, the green color, and the blue color. So we'll have 1 and 3. Okay, and this dimension will be C. Okay? And so we extend our 2D convolution to 2D convolution over multiple channels by just saying that now this kernel, it will also come with as many channels, so it will be also a tensor in 3 dimensions, where the third dimension will be the same as the number of channels in the input. So here we'll have 1, 2, and 3. And this will be C as well. Okay? And the outcome, the output now of this convolution, will be a map of size h, so this is w and h minus small h plus 1, w minus w plus 1. Okay? But what is important to understand also is that there is no third dimension for this output. Okay, even though we started from a tensor of 3 dimensions, C times H times W, and we had a kernel of size C times H times W, the output is not a tensor, a 3D tensor, it's a 2D tensor. Okay, because now what we'll be computing, so now we have this cube instead of this square that we place everywhere. Okay, and there is, if we say that the third dimension of the kernel is of size c, meaning the same as the input. Along this third dimension, there is only one position. Okay? And again, now we go from a double sum now to a triple sum, where we have also to iterate over the third dimension the number of channels. Okay, but other than that, we are still doing the same. If we flatten everything, if we flatten now these 3D tensors into vectors, these reduce to a dot product, and so we are still doing the same stuff. Okay? And finally, now that we have defined a convolution, we are ready to define a convolutional layer, okay? And we'll say that a convolutional layer will be defined by a set of k kernels. So here we had only one kernel, but we can say that we have several of them. Each one of them will produce one of these maps. And now if we concatenate all these maps together along a third dimension, okay, what we will obtain is a 3D tensor of this shape for the spatial dimensions, and the third dimension will be the number of kernels that we had. So in this case, k. Okay? So a convolutional layer is defined by a set of k kernels, uk, each of size c times h times w. Then we apply the 2D convolution operation to the input tensor x, which is a 3D tensor. Okay? And that produce key feature map, key output like this, each of size h minus h plus 1 and w minus w plus 1. Okay? But since we have k of them, so I'm just saying now we'll have another one here. Okay, so this is UK. Okay, and we have big K kernels. Okay. And now when we do the 2D convolution on using each one of these K kernel, each of them produce one of these maps. And when we concatenate everything, it means we'll have in total something like this, where this third dimension will be equal to k. Okay, so this is what you have also in this animation, where you see the three-dimensional input of size h, w, and c. You see one of those kernels. Then when you apply the 2D convolution, it's as if you were sliding over all possible locations. For each of them, you compute the sum of element-wise products, and then you report the value in the output. But you see that the output, okay, it comes with only 2 dimensions, the size of these maps. But then you can repeat that for another kernel, which you see quickly in red, like there, and that will just be, that the effect will be that you will be adding new slices to your output. Okay. So these convolutions, they also come with a few additional parameters, which you should know about. They are not that important, but practically when you will have to use these layers, these are things that you will need to set nonetheless. The first one is what we call the padding. So if you take some input, apply a convolution to it, the result will be a smaller image. An image where you will have, for example, reduce the width by the size of the kernel. You may be, in some cases, you may be interested in preserving in the output the dimensions of the input. To do so, there is a trick, which is just to say that actually around the image, the input image in blue, you do as if there were additional pixels, as if the image was larger than what it actually is. and you pretend, for example, that all these virtual pixels are set to 0, or that all these pixels have the same values as their closest neighbor, so whatever. And now, given this larger image, you compute the 2D convolution, and if you set the padding just in the right way, the result will be, or can be, an image of the same size as the input image. Okay? So here you see, for example, if you start from a 5x5 image, you have a 3x3 kernel. If you add a padding of 1, so you add one extra layer of pixels around the input, then the result now becomes a 5x5 image instead of before a 3x3 image. Okay. The second hyperparameter is the stride, which basically specifies a step size when you move the kernel across the input. So instead of considering each and every locations, you could say that you only look at 1 every 2 locations or 1 every 3 locations. Okay, and this 1 every n is what we call the stride. Okay, but this hyperparameter is actually quite interesting because the result of using a stride larger than 1 will be that you will be dividing the size of the output by the stride. So for example, if you have a stride of 1, you preserve more or less the size of the input. If you have a stride of 2, you will be dividing by a factor of 2 both the width and the height of the output. Okay, so you make it twice smaller. If you use a stride of 3, then you make it 3 times smaller. And finally, the dilation parameter, which will modulate the expansion of the filter without adding weights. So by that we mean that what if you want to look at a region larger, okay, without adding new parameters? So if you want to look at larger regions, because maybe you have more complex patterns, so you need more pixels, more inputs, you could just have larger kernels, okay, but that would come with a price, the price of adding parameters, okay, because you have to fill in all these values in these kernels. If you want to look at larger regions without adding these parameters, what you can do is to say, okay, it's as if you add a larger kernel, but you only look at a subset of its pixels, okay, and so this is what you see there with the 9 values. Effectively, we are now looking at a receptive field of size 5 by 5, even though the kernels has only 3 by 3 parameters. Okay? Okay, and finally, and then we'll take a break, equivariance. So I said at the beginning of the lecture that one of the inductive biases that we would like to try to enforce in a neural network is equivariance to translation. If we translate the input, we want the output to translate. Well, guess what? If you take a convolutional layer is equivariant to translation. If you shift the input, the output will be shifted. Okay, will be the same as before, but shifted. So formally, this is what we described in this way. We say that a function f is equivariant to another function g if the application of fgx is equal to gfx. So by that we mean, let's say f is some computation by a neural network, g is a translation. Okay? So we say that the output of the neural network on the original input, not translated, is the same as the output of the neural network on the shifted input, but up to the translation g. Okay, so you take your neural network, you produce some output, then you translate it. The result should be the same as taking your input, translating the input, and then feeding that translated input to your neural network. You should arrive to the same result. If that's true, then we say that we are equivariant to this transformation G. So when G is the translation, you shift a pixel, and F is a convolutional layer, then we can show that a convolutional layer is indeed equivariant to translation. And the mechanism that makes this possible is because we are effectively sharing the parameters, we are reusing the same parameters, so the same elements inside the kernel everywhere. Okay, and it's precisely because of that equivariance happens. Do you have questions on this? Nope? Okay, then let's take a break. We'll resume at 50, 55, something like this. Okay, continue. So just to summarize what we have seen so far, the main thing we have talked about today is the convolution, okay, and these convolutional layers. So what these convolutional layers do is to start from a 3D tensor with two spatial dimensions, the width and the height, a certain number of C of channels. And then from this input, this 3D tensor, you also consider a kernel, okay, which is itself a 3D tensor of smaller width, smaller height, but same number of channels, okay? And then we define a convolution. So as a tensor of size more or less h times w, okay? And each element in this output tensor is computed by doing this sum of element-wise products, which you should just interpret as computing a dot product on the flattened 3D tensors, meaning we are just computing a similarity score between some subregion of the input and the kernel. And if the two of them are similar, then that produces a high value. If they are dissimilar, then the score will be close to 0. Okay? One thing I've not really talked about yet is how similar are these computations to the previous kind of layers we have seen before, fully connected layers. So if you remember, a fully connected layer, we start from some input x, and then we map this vector to another vector, okay? For example, another vector h of size rw and of size rq, okay? And so I used to make these diagrams, and each element in this output vector h is connected by computing the sum, the weighted sum of the elements with the weights. Okay? Now you should understand that effectively it's as if we were comparing this entire input to this flat kernel, which is represented by this set of connections, by these weights. Okay? If you bundle all these connections together in a vector W, okay, this element, or Wi, okay, since we start from a matrix, we have that Hi is just the dot product of this vector with the input x. Okay, so in a fully connected layer, in a sense, we are also computing similarity scores. Okay, except that we use the entire input to make this computation, and that produces just one number. What is also different is that if you take another output element, hj, okay, this element j will be computed in a way which is similar as for hi, but using another set of weights, using other connections. Okay, so it's as if we were using another kernel in that sense. Okay, so this is what you have for fully connected layers. And if instead we have a convolution, let's say a 1D convolution, we still start from some input x, of the same shape. And then we produce some output. Okay. If I take this one, so H, and if I say that this output vector is the result of some convolution with this vector, okay? Let's pretend that we have a 1x3 kernel. 1, 2, 3. Okay. Okay. When we compute the convolution of this kernel U with this input X, okay, what will happen? It's as if we were, for example, for this location, using 3 input elements corresponding to this location I, and then we were connecting this subvector through weights. The first weight in yellow, the second weight in green, and the third weight in red. Okay? And then if we say that, okay, this other part, they don't exist, it's as if we were doing a fully connected layer on this small region. Okay? But so this would give us HI. But then what is really fundamentally different in a convolutional layer is that if you look at the computation of some other element in the output vector, Hj, we'll have something similar. So this element will have been computed starting from 3 elements in the input. But, okay, so here we had something like this for the second output. But now what is different from a fully connected layer is that we reuse the same weights. Green and red. Okay, so these weights there that we use to compute Hi, they are the same, they have the same numerical values when we compute Hj. While here, when you compute the output J in a fully connected layer, these weights there, they are not the same as the weights connecting I. Okay? So this is what I said before the break. This is what we call weight sharing. Okay? We reuse the same numerical values. We share the weights. Okay? And this is because of this weight sharing that we have equivariance. Okay? So you see that a fully connected layer and a convolutional layer they look very similar, right? In terms of what they compute, both of them are just weighted sum, dot products, maybe on some smaller part of the input for the case of the convolutions, and we have this additional weight sharing parameters, this weight sharing mechanism, but other than that, it seems that a convolution is quite related to a fully connected layer. And actually, you can show that a convolution is just a special kind of a fully connected layer. Okay, so if we take the entire output, H of a fully connected layer, we have something like this. Okay? Now, what I'm asking is, can we re-express the computation of this output in this way? Can we express the convolution as a matrix times a vector product? What do you think? Projecteur de gauche. So can I re-express a convolution as a fully connected layer? Yeah. Yeah, regardless of the bias. Yeah, actually, in the previous expressions, I think I've removed them, but you could add an additional bias parameter if you want. But let's say we don't have bias terms in a fully connected layer. Can we express then a convolution as a matrix times a vector operation? Yeah. Mm-hmm. Yeah, exactly. That's the idea. So H times W X plus B. Okay. So H, the output, you agree it's a vector. Right? And I'm saying, okay, this output vector is the result of a matrix W transposed times a vector X. Okay, plus some other vector, the offset. Okay, so the question is, can we mimic what we are doing when we compute a convolution by defining some matrix W transposed, which would give us the same output? Okay, so let's think. When we look at, for example, this first output, this first output is computed by taking this subregion in the input and then multiplying this subregion by the kernel elements, and then we sum everything. And that's how we compute this. Okay? So that means to compute this element in terms of a matrix times a vector product, I would be multiplying this. I would be computing the dot product between this row and these columns. Okay? But if I want for this product to be the same as what I compute when I have a convolution, well, what I could do is to say that the first value there in the weight matrix corresponds to this yellow value, okay, this one. Then the second is the green, and then the third is the red. Okay, and then outside, for everywhere else, at all the other positions, I'm just putting zeros. Okay, if all these values are equal to 0, then when you multiply yellow with this element, and then green with this element, and then red with this element, and then 0 with this element, 0 with this element, effectively we'll just be computing the dot product between these three colors and this part of the input. Okay? Which is just what we compute when we have a convolution. Okay, so that's for the first row. Then for the second element, this one, well, this one is computed by looking at this part of the input, and which you multiply by the same weights, okay, but at a different place in the weight matrix. So now what we will have is that for the second row, we have this. Okay, and 0 everywhere else. And then you guess what you have for the third. Okay, and so on. Okay. So if we fully instantiate this matrix, we have some kind of diagonal matrix, but where the diagonal is not made of one element, it's made of several elements, as many as we have in the kernels. So everywhere outside of the diagonal of this block diagonal, you have zeros. But what is nice is that now when you multiply this matrix with the inputs, you recover the same output as if we were doing a convolution. Okay, so this is just showing that yes, convolutional layers, they are just a subset of fully connected layers. Okay, because with a fully connected layer, we are just saying, okay, we multiply this input vector by some matrix, and then we add some offset. Okay, and then I've just shown you that a convolution is just the same for a specific choice of W. Okay, then I will have a trick question. If a fully connected layer, so if you agree with me that a convolution can be represented as a fully connected layer, why do we have convolutions at all? It seems to me that a fully connected layer will be strictly more powerful because it can compute anything that a convolutional layer can do and more. So why do we care about convolutions then? Yeah. Yeah, that's a very good element. So if we want to, so for example, for this entire matrix, okay, actually we have only 3 parameters, which is much smaller than the dimension of this matrix. What else? Yeah. Yeah, but I mean, if the fully connected layer converge to this matrix, it will be equivariant too. So why do we do that? So your intuition is correct. Okay, you say, but it's because we want equivariance. And I just said, okay, but we may get it if the fully connected layer converge to that. But that's a big if, actually. Because for the fully connected layer to discover this matrix, you would need basically to see all invariant, all translations of the input, which is unlikely to happen in your training set, for example. You will not consider all translation of your input images when training. You will consider one of them. Okay? So the idea is to say, okay, we have some assumptions, we have some properties that we want to enforce, and we'll try to enforce them from the beginning, directly inside the architecture of the network, such that then we don't have to care or we don't have to rediscover them during training. It's still possible, but you would need very large data sets for this to happen. Okay, so in this next slides, you have the mathematical derivations, which shows you that indeed you can re-express convolutions as matrix multiplications. So the example I take is you start with a 4x4 matrix and a 3x3 kernel. Their convolution is a 2x2 matrix. Okay, and you can re-express this in a way similar to that thing. What you need is to start from the convolutional kernel and then rearrange this kernel in what we call a sparse two-pleat circulant matrix. So it's a matrix which, so the dimension of this matrix, so the number of columns correspond to the number of input elements. So you see here we have 16 columns because we started with a 4x4 input. Okay? Then each row corresponds to one of the possible outputs. So in this case we have 4 rows because we have 4 outputs. Okay? And then you fill in the values of this matrix by just the values of the kernel elements, okay, only for the positions corresponding to the corresponding region in the input. So in this case, for the first output, we have to use this region, okay? So that means for all the elements outside of this region, so 7, 8, 4, 8, 7, 5, and 6, they are not used in the computation of this output element. So in this case, you will set all these positions to 0. The values at all these positions to 0. Okay? And all the remaining values correspond to positions at which we multiply the input with the kernels. Okay? And we just report the values of the kernel. Okay? So you do that for all possible locations or all possible outputs. Then you say that your input x is flattened. So, okay, so you start from, for example, your 2D matrix. You flatten it into a long vector, okay, which is in this case is a column vector. And then you say, okay, if you compute the matrix vector product of this matrix U, the convolution matrix, with this flat vector, what you obtain is the flattened version of the output of the convolution. Okay, you can yourself recompute these values. You will see that we recover the values that we obtain for the convolution, and then you just say that you reshape this vector to the appropriate dimensions. So you go from a flat vector to a 2x2 matrix. Okay? You can generalize that to arbitrary sizes, but it's still more or less the same idea. Okay? What is important is eventually to understand that this operation, the convolution of x and u, is equivalent to this matrix times a vector product. Okay? And because of that, it's equivalent to a fully connected layer. Okay? Okay, then I have a question for you, or maybe after this one. So this is another representation of fully connected layers against convolutional layers. Here you have in A and B a fully connected layer. So you have some input vector X, output vector H. Here you have the weight matrix, W. Okay, so you have, so for example, the first row corresponds to all the weights connected to H1. So starting from the input and then arriving to H1, and so on and so forth. So you see that you have a dense matrix. If you compare that with a convolution, okay, you can also represent that as you can represent these weights also as a matrix, where, for example, to produce H1, you have weights starting at X1 and X2. Okay, these two connections. For H2, you use instead X1, X2, and X3. So these 3 input elements are themselves connected to 3 weight values, which are reported there in this matrix, in the second row of the matrix. What you see also, another difference is that all these rows, they contain the same values. The weights are shared. Okay, you have dark brown, light brown, and you reuse the same values. Okay, this is different in a fully connected layers where you have parameters for each input-output pair. Okay? And this is what you would have when you have a convolution with a stride of two, sorry. So where you skip some of the possible locations of the kernel on the input. And so in this case, you see that you have fewer output elements than before, okay? But it's as if you were skipping some of the rows, okay? You start from this matrix, you skip this row, you skip this one, okay, and you skip the last one. You have a smaller matrix, but if you multiply this matrix with input, you recover this output vector. Okay? Okay, another inductive bias I talked about is this concept of locality. Where do you see this concept being enforced in these diagrams? Yeah. Yeah, exactly. So it's because this matrix is sparse and it's a band diagonal matrix, okay, that we have sparsity, that we have locality. Because to compute this H2 element in the output, we are only using a small subset and local to some local subset of the input elements. If instead we want to make this convolution less and less local, so more and more global, what would happen is that we increase the size of the kernels, and eventually, when the size of this kernel corresponds to the size of the input, you recover a dense matrix here. Okay? Yeah. Okay, trick question. So 2 weeks ago, we talked about reverse mode autodiff to compute gradients. So how do you think we actually tune the parameters of a convolutional layer? Okay, I have one solution, then you tell me if I'm wrong. I've just told you convolution can be expressed as a matrix times a vector product, right? And a matrix times a vector product is the same as a fully connected layer, except that we'll have this spatial structure for the weight matrix. Okay, but I could just say this is a fully connected layer, and I know how to differentiate a fully connected layer. We've seen that 2 weeks ago. So one possible idea would be to say, I start from this kernel, I instantiate this matrix, and then I do as if this was a fully connected layer, and I compute my gradients, and then I make my updates on this weight matrix. Yeah. Yeah, so if we do that, this is what would happen, and you're entirely correct. If we instantiate this matrix and say this is our matrix of parameters, and then we update them independently as if they were like a fully connected layer, then maybe we would make an update for the yellow color at this position, but this update maybe would be different for these other values. And if we were to do that, then we would lose this property of weight sharing. Okay, so this is not how the backward path of a convolutional layer is implemented. I will spare you the details, but actually you can show that the backward path is also convolutions, but on the gradient values. And that's how you implement it. All right. Do you have questions about this first part? Nope. Okay, so let's move on to the next part, which is about pooling. So convolution, you should really understand them as some feature detector. Okay, you have a feature which is encoded inside the elements of the kernel, and you try to detect it somewhere on the input tensor. Okay, pooling is something a bit different. Pooling or pooling layers will be a kind of layers that we can use to reduce the dimensions of the input. Okay, so when you have, for example, a very large input image, there are cases where you would like to reduce the dimension of this large input image. Okay, but you want to make this reduction in a way which makes sense, and one way which makes sense is to say that you want to preserve the global structure of this large image. If you make it smaller, you want to still see more or less what was the original content. Okay, so exactly as what you would do, for example, when you open an image in an image editor and then you resize it. If you resize it to smaller dimensions, you still want the structure to be preserved. Okay? Now the question is, can we have something really similar in a layer? So this is what pooling layers implement. There are various ways to define this downscaling operation. Here you have two of them. So let's say we start from a tensor of 3 dimensions, so a certain number of channels, and then some 8 and some dimension. And we say that the 8 and the width can be divided by R and S. Okay? We also say that we will have a pooling area of size small h times small w. And then we say, for example, in the case of a max pooling layer, that the output of a max pooling layer will be a tensor of size C times R times S. So you preserve the channels, but you reduce the 8 by a factor H and the width by a factor W. Okay? And you say that each element of this output tensor, so the element at position Cji, is simply, for example, the maximum element in this subregion, of the input. And this input region is of size h times w. Okay, so this diagram maybe will make things simpler to understand. This is your input, and in gray you see the pooling area. Okay, so you consider a pooling area of size WH, as I said. Then for for each position of this pooling area, you compute the maximum element, and this maximum element, you report it into the output. What's different from a convolution is that you don't consider overlapping regions of the input. They are disjoint. Okay, so it's as if we were using a stride equal to the dimension of the pooling area. And that's really important because this is because of this stride, as we have seen for the convolutions, which is larger than 1, then we manage to reduce the size of the input. Okay? The other kind of pooling mechanism we could use is just to compute the average value instead of computing the max value. Okay? Okay, so why do we care? Why is this interesting? Other than just reducing the dimension of the input. Because one of the properties that you get by doing pooling is invariance. So we saw before that with a convolution, you get equivariance to translation. With a pooling layer, you will get, at least locally, permutation invariance. So what does that mean? We say that a function f is invariant to another function g if the output of the function on the general input is the same as the output of that function on the result of g. Okay, and a pooling layer provides that. It provides invariance to permutation inside within each position of the pooling area. Okay, so for example, if this is our input, okay, and then we do a max pooling operation with a pooling area of size 3, okay, we get an output vector of size 4, okay, we go from 12 to 12 over 3, so 4, and each output element, for example, this one is computed by taking the max of the element within this pooling area, okay? And what I'm saying is that this is nice because this gives you permutation invariance. What does that mean? Is that if you permute the element, the pixel values there inside the pooling area, and then you recompute the pooling values, you will get exactly the same. Okay, so if you shuffle these pixels, it's not, you will get the same results. At least if you shuffle them locally, of course. If you shuffle everything, you will get a different result. Okay, and what we'll see is that this is really important because, or this will be helpful because we'll manage to use this mechanism to detect the presence of a pattern somewhere, regardless actually of that location. Okay, so let's see how that works. Or let's see now how we can compose these two new layers into convolutional neural networks. So the architecture that you should have in mind is should follow this template in which we say that a CNN, a ConvNet or convolutional neural network, is defined simply as a composition of convolutional layers, pooling layers, and everything else we have seen before. So fully connected layers you may have also in CNNs, and also nonlinear activation functions. But usually what we'll do is to follow this specific template that you see in the figure, where you have, for example, a first layer of convolutions with a certain number of kernels. So you will produce different variations of this image because you are looking for patterns, okay, which will be detected by these kernels or implemented by these kernels. And then, okay, if you remember that I said you should interpret these convolution values as a similarity score, and then if you combine this output that we compute by a convolution with a ReLU, for example, what you will say is that you only keep these locations which are, for example, sufficiently close or sufficiently high or sufficiently similar with these kernels. Okay? When you apply a linear rectification, so ReLU activation, you basically set to 0 everything but the values which are positive. And if you insert a bias term additionally, then you can control for how large you want the similarity to be moved forward inside the network. Okay? And then, so you can have several of these convolution ReLU. Usually you have one or two of them, and then usually they are followed by a pooling layer. And the effect of this pooling layer will be to reduce the spatial dimension of the feature tensor. And then what we do is that we continue in the next part of the network by having more convolutions and more linear rectifications and then more pooling layers. So let's say this is the input, okay, and we have a cat again. Okay, or you can draw something else, it does not matter. Let's say we start by a first convolutional layer. Okay, and we say that we have kernels U, K, of size, I don't know, 3 by 3. Okay, so these kernels, they will look at very small regions of the input. of size 3 by 3. Okay, so we may have, for example, a first kernel like this, which will be 1, 1, 0, 1, 1, and then 0, 0, 0, 0, 0, 0. Okay, and this kernel will be trying basically to detect short vertical lines. You agree? So that means, for example, the output value for the kernel, for the convolution, will be high for this very specific region, and maybe high also there, I don't know, or high there, and so on and so forth. Okay? So that will produce, this kernel will produce a first output feature map. Okay? If we have more than one kernel, and usually that's the case, maybe we would have another kernel encoding for horizontal lines, okay, or small horizontal segments, then this would also produce another map where we would have so in a sense what you would have here is the something like this maybe, where you keep everything which is more or less vertical. Okay, everything else is set to 0, and there you keep everything which is more or less horizontal. This part of the nose, something like this. Okay? We may have, let's say, another one. Where we have this diagonal, and here that would produce another map where we keep everything in that direction. So we'd have this part of the ear, something like this. Okay. So these values, they would not be 0 or 1, okay? They would be something, they would be just real values that you get by computing the dot product, okay? And so what happened is that then we say that we feed these values to a nonlinear activation function like a ReLU. Okay, and the effect of this ReLU will be to only keep those values which are large enough. Meaning you will only move pass forward the locations in a sense of the input element of the locations in the input that are sufficiently close to each of the kernels. Okay? Now you recombine all of this feature map into a 3D tensor of side. So you could preserve the spatial dimension, but now the number of channels would not be the same. The number of channels would be the number of kernels that you have used in the first convolution. Okay? So when you recombine, you get a bunch of maps like this, and you have k of them. Okay? Now, we could follow that with a pooling operation. And the effect of this pooling operation will be, for example, if you use a 2x2 max pooling, would be to reduce by a factor of 2 this tensor. Okay, so we'd go from something like this, and we would preserve the number of channels. Okay, but these spatial dimensions, they are twice smaller than here. And then what is interesting now to understand is that what happens when you do next a convolution on this tensor. So let's say now I do another 3x3 kernel, whatever that is. What will be first? So to what region? So how to tell? So now if you do a 3x3 convolution on this reduced tensor, can you tell me to which pixels in the original input you will effectively look at? Yeah. Exactly. So that's so. When you do a convolution after a pooling, okay, even though we keep small kernels of size, for example, 3x3, it's as if, since each of these values has been computed by a larger region, it's as if we were looking at larger region in the input. Okay, so this, for example. So originally we have that this 3x3, they look there, okay, at this small region. But this one, this 3x3, because of the pooling of size 2, will be looking there at a region which is larger. Okay? So this composition of convolution pooling allows you to look at larger and larger regions in the input in the input. Yeah.
Don't we lose the concept of locality by looking at bigger regions?
Yes. Yes. Yeah. So with this effect, we are effectively looking at larger and larger regions. But there is another effect which is about the composition of patterns. So since each of these slices is the result of the detection of some feature, when we do the convolution on this tensor on its reduced version, now this kernel would not be looking anymore on one specific pattern. It would be looking, because we are also looking, we consider, we aggregate across the channel dimension. Okay, we are effectively looking, so this, yeah, maybe I should add it there. So this is of size k. This kernel now will be looking at combinations of features detected by the previous layer. Okay, so we start from simple features like lines, but then already in the second, you can have something like compositions of vertical and of horizontal and vertical lines. Okay, and that's how then you have the emergence of more and more complicated patterns simply as a composition of simpler ones, exactly as in the model proposed by Huber and Wiesel, where you have these hierarchical compositions of simpler and complex cells. Okay. Okay, so this is another template for a CNN, but it follows what I've been talking so far. You start from some input, and then a good recipe just to have convolution ReLU a certain number of n of times, followed by a pooling. Then you repeat this whole thing several times. Okay, and then once you think you have features that are good enough, you flatten everything, and you concatenate that. You concatenate your architecture with an MLP. Okay, so the next layers will just correspond to an MLP, where you have fully connected ReLU, fully connected LU for a certain number k of times, and finally you have the output layer of some dimension, depending on the problem that you want to solve. Okay, so this is an example of that, where we start from an image, a picture like the picture of an animal. Then we have a first layer of convolutions. Okay, and you see that we have these grayish patterns, which correspond to regions that are more or less similar to the corresponding kernel. Then we have this second column, which corresponds to the output of a ReLU. So basically, we only keep what is high enough. Okay, which is so these values, these regions, we only keep the activations which are large enough. Okay, which such that after the ReLU they are preserved. Then there is another convolution, another ReLU, and the fifth column corresponds to a pooling operation where we reduce the spatial dimension. And then you see that what we do is that we replicate this bunch of 5 layers 3 times, 1, 2, and 3. And we arrive at the end to something very pixelated, which you see there, which correspond to features. Then you flatten everything. That gives you a big vector. You feed that to an MLP. And the last layer of this MLP is as long as, let's say, the number of classes that you want to predict. And then you look at the top predictions. Questions on this? Okay, let's do a break then, and then we'll continue with the demo where I'll show you that in code and with another demo. We'll resume in 10 minutes, 55. Okay, so just to quickly recap, what we've seen so far are the convolutional layers. Then we talked about pooling layers to reduce dimensions. And more interestingly, we talked about the compositions of these two together to produce convnets as the one that you see there. Okay. What I will show you now is 2 demos. One to, again, just try to develop your intuition about what's going on in this kind of neural networks. And then I will show you how to actually build and train one of them. So there you see a neural network very similar to what I talked about. You have an input image. You see that you have 3 input images because in this case you have 3 channels. Okay, you have the red, the green, and the blue channels. And then you have this bunch of layers. The first one is a convolution followed by a ReLU. Then the third one is a convolution followed by a ReLU again. And finally, you have a pooling layer to reduce the spatial dimensions of the feature map. And then it continues. You have a convolution ReLU, pooling. And finally, you flatten everything. You have a fully connected layer which you map to your classes. Okay, to produce a vector of probability values associated to each class for the input image. Okay. If I take, for example, this, so this corresponds to one kernel in the first convolutional layer, and you see that this one is computed by where is the kernel? Yeah, it's this very small thing that you see there, the small square. So the part of the kernel associated to the first channel, the third channel, and the second and the third channel. Then you multiply, you do this one-dimensional, two-dimensional convolutions using this slice of the kernel on the corresponding slice of the input. That gives you these maps. You sum everything. That gives you this output. Okay? Here they are just decomposing the computation over the channels into per channel operations. And you see there also that you may insert, this is not something I've talked about, but which we have quickly mentioned. You can also add a bias term at the end of the convolution results. Okay? If I take another one, I don't know, like this one, okay? It's the same kind of computations, but now since the kernel is different, it will activate differently the input, it will respond differently to the input to produce another and distinct output feature map. Okay? Then you have the ReLU, okay, where the ReLU, if you remember, is just the max between 0 and the output. So, for example, there, everything which is orange or red is negative, everything which is blue is positive. So when you pass this thing which is mostly red, mostly negative, almost nothing comes out, except maybe this part which is more blue and which is preserved after the ReLU. Okay? And of course, you see that, so for example, there, you see that you only keep the blue. Everything which is orange is erased from the output feature map. Okay. Then let's take the second convolutional layer. Now it's a bit different because this convolutional layer works at the level of the previous output tensor, okay, which is now a tensor in which we don't have 3 channels anymore, but 10, because we had 10 kernels in the first convolutional layer. Okay? But it's the same story, except that now we have more channels in the kernels and we have more channels in the input. Okay? But that at the end produce a slice per channel. We map everything that produce this final outcome which you see there. We pass that again through ReLU. For example, if I take this one, and again, everything which is negative is removed, and everything which is positive is preserved. Okay? Then comes the first pooling layer, where we just do a special reduction of the input. So here they do a 2x2 reduction, and you should see that this is more pixelated than this one, because indeed the resolution is twice smaller. Okay? Then we have here the second the second block of convolution and pooling, which now works at the level of this smaller resolution input. Okay, and then you iterate like this. You go through the network to produce the final. Let's take this one. So this is a cup of coffee, and you see that the class espresso is associated to high probability. And so you should basically consider that you flatten this entire, all this image into a very long vector. This is what you get there. Okay, but you don't see everything because it would be too large. And then you have the final fully connected layer in this part. Okay, and then you feed that to the softmax. Okay, and if I change same network, so same kernels, but I change the input, then it responds differently. Okay, and in this case, so this is a ladybug, coccinelle in French, which is mapped to the corresponding class. Okay? Okay, so in terms of code, how would this look like? So if you have not started the homeworks, if you have started the homework, you should be already quite familiar with PyTorch. If not, then a reminder is that the deadline for the first homework is on Sunday or Monday. So it's time to do it. It should be fast. But so what I will do is to try to train a neural network on this MNIST dataset, which maybe some of you know already, which is this these images of handwritten digits. And the goal is to take an image and to classify this image to the corresponding digits. So given this image, we want to produce a classification output with the label 4, label 3, label 9, label 8, and label 8. Okay? And that's a bit difficult because there are many ways these digits can be written. Okay? So I will show you two networks to solve this task. The first one is just a regular MLP, as we have seen 3 weeks ago, and the second one will be a CNN, as we have seen today. So for the MLP, well, I'm just doing as usual. I define a sequence of layers. The first one is a linear layer, mapping my vector of size, input size, to an hidden n hidden values. So the first hidden layer has a size of n hidden, which is set to, where is it? Yeah, that will be an input of the constructor. Then we have a ReLU, another linear layer of the same width, a ReLU, and a final linear layer, which is mapping back this number of hidden values to the number of classes that we have, okay, which is the output size. I'm not adding the final softmax because this will be taken care of directly by the loss that I will use. So this will just produce the values before the softmax, which we call the logits, and I will use that. The forward pass that I have to implement to specify what's the output of my neural network is just given by this simple 2 lines of code, where first I flatten everything, because for an MLP there is no spatial structure, everything is just a vector. So I'm flattening my image into a big vector, and then I feed this image to my network, which I've defined before. Okay, and I will pass that as an output. For the CNN, we have something a bit similar. I define now a sequence of layers, except that I will be using convolutional and pooling layers. So I do as I told you to do. I have a first convolutional layer, then a ReLU, then a pooling, then a convolution, then a ReLU, then a pooling. Then I flatten everything into a big vector, and I follow that with a very shallow MLP, in this case just one fully connected layers, a ReLU, and then again I'm mapping that back to the output. Okay? What is important also for you to realize is how do you set the number of kernels. So in PyTorch is by saying, specifying the dimensions of the number of channels in the output. Okay, so you will find this argument out channels, which correspond to the number of channels that you want as an output, which effectively amounts to saying how many kernels you want to use. Okay, and I'm saying that I'm using in this case kernels of size 5 by 5. Okay. For the training, this will be the usual training loop. I will be using Adam on the model parameters. And then I have a certain number of epochs. And at each epoch, I'm iterating over the entire training set. And at each iteration given by the loader, I consider a mini batch of elements that I will remove for now. Where, what do I do? So I reset the gradients, I compute the predictions by passing the data to my model, I compute the loss, in this case the cross-entropy loss, for which you need the logits, so the output of the neural network just before the softmax, and the target values, so the target labels. Then I do reverse mode autodiff by calling backward. This will be computing the gradients, and once the gradients are computed, I do a step using the optimizer. Okay. Then I have some piece of code to evaluate okay, I should keep that actually. Okay. So let's do a first experiment where we'll just be training the MLP. Okay. So I set the input size to the size of the image. In this case, they are 28 by 28 pixels. So I will have long vectors of 700 elements or so, 10 outputs. I will be using layers of width equal to 8. Okay. Then I instantiate the network. I count its number of parameters just to give you a sense of how big or small this network is. Then I train and then I evaluate. Okay, so if you take this MLP, you train on MNIST, you do 10 epochs. Over the training set, you see that indeed the cross-entropy loss decrease as you train. Okay, there are some fluctuations. And after 10 epochs, you reach an accuracy of almost 90%. which is not that bad. Okay, with only a random classification would have an accuracy of 10%. Now, if you compare that to the ConvNet architecture, where I'm using 6 kernels for the convolutional layers, you see that I have the same number of parameters, about 6,000 of them. Okay, and after 10 epochs, we reach an accuracy of 95%. Okay, so in this case, it's slightly better. We gain 5%. You may tell me, okay, but that's not that big. Is it really that important? It's in this case, it's because of the training set. It's very easy. But if we had more variations, the task would be much more complicated for an MLP to solve. And in this case, what makes the MLP to have good results is that all these images, all these digits, they are always, for example, at the center of the image. Okay, but if we had digits everywhere on the input of the image, then the performance of the MLP would decrease by quite a lot. Okay, then second experiment, I want to show you what would happen if you shuffle the pixels. So I'm taking the same data set. I define a random permutation of the pixels, which I apply consistently to all the images. Okay, the same permutation. And then I train an MLP first, and then a CNN second. How do you think the result will change or not? Yeah. Okay, who agrees with that? Okay, can you elaborate why you think that will happen? Mm-hmm. And why? Okay, so these are, let's say, we take these 5 images, we apply the same permutation. This will be the training data for these 2 networks. Okay, and why? So you're entirely correct. And why the CNN would perform much worse is because now we are breaking the locality assumption. Okay, when we train and build actually the CNN, we said there are local patterns to be detected. But if we shuffle randomly, we are basically destroying this information. Okay, which means that now if a CNN tries to classify these shuffled pixels, then it's making its prediction on a wrong assumption and therefore will not manage to solve the problem. So let's see if that's really the case. Okay, you see that there is a 10% decrease of accuracy. And if you, if you used smaller kernels, that would be even worse. If, on the other hand, we train the same MLP as before, for which we had 89% of accuracy, okay, you see that the performance is almost the same. Okay? So this is an important lesson. It's very interesting to put inductive biases, like locality, composition, and other things. And the advantage is that the neural network doesn't have to relearn or rediscover these things if they are important to solve the task. And because of that, that means from a small data set, you will be able to do quite well. On the other hand, if you put some inductive biases in your architectures, but these inductive biases are wrong, okay, then you are shooting yourself in the foot, okay, because you are forcing the network to do something which is wrong. All right. Let me switch to this. Do you have questions about this? Okay, then the next part will be quicker. I just want to give you a few comments about architectures that exist in deep learning, CNNs and others. So if you look at the literature on CNNs, you will see that there are dozens, or if not hundreds, of architectures which have been proposed these last 10 years, and you see a few of them. So they are different with respect to their size, so how many parameters that you have. In this case, it's indicated by the size of these circles. The larger the circles, the more parameters you have. The number of operations that you need to perform to compute the output starting from the input. And finally, the accuracy that you get on a benchmark dataset, in this case, the ImageNet dataset. And so this picture is already quite old, but so it's from 2018, but already you could see a few trends. So usually the bigger the networks, the better. You see that these larger bubbles, they are usually close to the top. Not for all architectures. You see that this one, even though they are big, they are not at the top. You see that this neural network may require a certain number of operations, which is not necessarily positively correlated with the quality of the output. So it can be the case that the more operations you do, the better, and indeed you are there in this there. But it's not always necessary. You can often reach high quality predictions with much fewer operations, and you see that many models are there on the left, for which only a few, it's in gigaflops, so it's millions of operations, but fewer, I would say, and still reach good results. Okay, and this is actually an interesting question that the field is asking. Can we reach good results with few resources, with limited computational resources? And you see, for example, a few names like MobileNet, which a few years ago was used on mobile phone, so where you wanted to have a CNN directly running on your phone, where the resources are limited, so you want something which is accurate, but also lightweight in terms of operations. Okay, just historically, I will comment on a few architectures specifically. This one, le Net 5, is an architecture which was proposed by Yann Lequin. It's quite old, from the 90s. But it's just to show you that it's really instantiating this template I was talking about. You start from an image, in this case a 28 by 28 pixel images, grayscale, followed by a convolutional layer, in this case in which you have 6 kernels, so it's producing 6 feature maps. Then there is a pooling, then there is a convolution, there is a pooling, and finally a few dense layers, like in an MLP. Okay? And of course, you may have also, after the convolution, nonlinear activation function. They are just not shown in this architecture. A question. So this network looks very simple, and indeed, that's very simple and very primitive if you look at what we are doing now. But already with this simple architecture, you could actually use that in actual systems. So this very network was used for several years by the US Postal System to scan letters on which you had handwritten addresses, for example, and they had to be recognized. So this is a short video showing Yann Lequin at the end of the 80s, then showing a piece of paper to a camera, and then applying his CNN to detect all the digits. And you see that it could work for several variations of these digits. Yes? Oh, sorry, again, it's a bit big. Thank you. Okay, there you go. Then it's applying locally the CNN on small regions of 28 by 28 pixels. And then for each region, it recognizes the digits. So this one is LeNet 1. It's an older version than the one I've shown you, but it's not that different. Okay, no, as usual, in a group you have one doing the work and the other watching. Okay. What is interesting also in this architecture is something also you will see if you study this architecture. One thing that you may notice is that as you go deeper in the architecture, usually what will happen, something we do when we design this CNN is to increase the number of kernels. So you see that we have 6 kernels there, and then 16, and then 16, and you will see later on other variations of this architecture where, as we go deeper, we make this, we increase this number of kernels. Do you have an idea why this is a good idea? Why it's a good idea to increase the number of kernels as you go deeper in the architecture?
Because we are doing polling and the matrices are smaller and we have less operation.
It's true that because of the pooling, the spatial dimension will decrease, but I'm also telling you that at the same time we will be increasing the channel dimension. So in total, it will not necessarily be smaller. And so in terms of compute,
But it will be smaller to do it when we go deeper instead of doing the beginning.
depends, because each convolution will have to go across this longer and longer number of channels. Yeah.
Maybe if we have a bit of information vanishing on the forward path, but vanishing more kernels, and more information.
Maybe. Yeah. 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 Mm-hmm. Mm-hmm. And yeah, that's exactly that. So usually we increase the number of kernels because, as I've told you there, now this kernel will be looking at a composition of previous features detected. Okay? And so there is only so much simple features that you can detect, but as you go deeper, you will be composing these features into more complicated patterns. Okay? And so if you count the number of compositions of the simple things into complex things, that will quickly blow up. Okay? And you want to discover these combinations that are, of course, interesting for the task that you want to solve. Okay? But since there are many more ways to combine these features, usually we account for that by increasing the number of patterns. Number of kernels, sorry. Also, very often at the exam when I ask this question, so something that I like to do is just to ask the students to instantiate a CNN or something like this. And 1 every 2 students just tell me I would use 1 kernel. This is a terrible idea. Can you tell me why? So I would use convolutional layers with one kernel. Yeah, because it means that then you will be trying to solve the task like classifying or recognizing an animal from one feature only. Okay? There is no way you will be able to do that. Okay, let's move on. AlexNet. So AlexNet is an architecture which was proposed in 2012. It's quite famous because it won an important challenge in computer vision, the ImageNet challenge, and it won this challenge by quite an improvement from 1 year to the other. And it was also the first time a computer vision benchmark was really beaten by a pure neural network approach. Before that, researchers used to basically think about features and handcrafting features, programming features manually, and then evaluating all these features on the input images, and then feeding this vector of features to a traditional machine learning model like an SVM or decision tree or something like this. There, everything was completely thrown away. You just have a big neural network and deep, which you train for very long on a large data set. And it showed that it was, in this case, it yielded the best results. On the diagram, you see a comparison between LeNet and AlexNet. It's quite similar, just deeper and larger. So it's a composition now of 8 layers with a 3-layer MLP at the end. But other than that, it's the convolution, pooling, convolution, pooling, convolution, 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 pooling, and then the MLP. Then, starting from 2012 onwards, basically the entire computer vision community said, okay, there is no way we'll be able to keep up with our handcrafted features. So the entire community switched to neural networks. And for the next few years, this competition, which was held every year, was won every year by neural networks. So this is another one which was made popular through this challenge, the VGG architecture, which is, again, just you take the same recipe, but you make the neural network bigger and bigger. In this case, the depth of the network goes to 18 layers. But other than that, it's more or less the same recipe. You have convolution, pooling, a bunch of convolution, a pooling, and then you define this in a block. You repeat these blocks several times, and then you follow that with an MLP. Yes? That's a good question. Yeah, I think it's the number of kernels. Yeah. So you see, actually, that's related to what I was saying also. Here you start with 96 kernels, and then 256, and then 300. So you increase the number of kernels as you go deeper in the architecture. This was for AlexNet. And in this architecture, you don't see them. They are not mentioned, but it's the same. The effective receptive field, that's something we've already talked about. Okay. There is an interesting observation. If you compare this architecture, the VGG architecture with AlexNet, you will see a difference in the size of the kernel. Okay? In AlexNet, they use very large kernels, 11 by 11, then 5 by 5. 11 by 11 is quite large. And in the VGG architecture, which performed better, they were using smaller kernels. Okay, so that may seem counterintuitive. If you make this kernels smaller, it should be worse. But that's actually not the case. It's because if you compensate your smaller kernels with a deeper network, you will have this effect which will kick in several times. Okay, and as you go deeper, the effective receptive field of the element will grow bigger and bigger. Okay. So that's why, in this case, it's better. So this is what you have there. What is important is that the size of this effective receptive field, it grows linearly with convolutional layers that you chain. Okay, but if you then add in between convolutional layers, you add pooling layers, then it will grow exponentially with the number of pooling layers. Okay? And this is what you see there in this sequence of layers, where we would have a first convolutional layer, and you see that the receptive field of this neuron is given by these three elements in the input. Okay? And we have three kernels, so we have three columns. Then if we add a next convolutional layer, which input is the previous layer, okay? And we have again 3 by 3 kernels of size 3. We look at these elements, but since each of these elements is itself computed from 3 inputs, okay, what will happen is that the effective receptive field, for example, of this element will be of size 5. And you see that it increases, in this case it increases linearly because we are not interleaving these convolutional layers with pooling layers. If you have a pooling layer or equivalently a convolutional layer with a stride larger than 1, like a stride of 2, that will reduce the feature dimension. In this case, these elements, they still have the size of the receptive field still increase only linearly, but what will happen next is that when you add a fourth layer there and you look at the effective receptive field of this neuron, now they will be much larger, in the order of twice larger. Okay, and then at this point, the recipe was basically the deeper, the better. And so in 2015, it was the ResNet architecture which won the challenge. And really the recipe is simple. You just scale, you increase the depth as much as you can. In this case, they won the challenge by scaling the depth of the network to 152 layers. Okay, so it's very deep neural network. Unfortunately, if you do that a bit naively, at least from the blocks that we have seen together so far, you will not be able to train this neural network. Even if you use ReLUs, even if you initialize properly, even if you do everything as we have discussed, for a neural network which is that deep, you will still have usually vanishing gradients. So the trick in ResNet is to add so-called residual connections, in which basically we say that so if this is a segment of a regular where is it? So if this is a segment of a neural network where you have, for example, convolution, ReLU convolution, and other things, these batch norm things, just don't pay attention to them. They are not really important. And then a ReLU. If you stack many of these blocks or these layers, you will have vanishing gradients. Okay. In ResNet, what is done to fix this problem is to add residual connections, and which is to say that the output of this entire block of layers, okay, is given by the input itself plus the output of the block. So you say that if you have X going there, and you have the output H, okay, what you do, so usually you would have your neural network like this, and you say that H is equal to the output of the neural network evaluated at the input, okay? If you say you add a skip connection or residual connection, you do something like this. And you say that H now is equal to the input X plus the output of the neural network block. And the nice thing, if you do that, is that the gradients, when you do the backprop, the reverse mode autodiff, it will have to go through this neural network block as usual. But since we use the total derivative, it will also go through this path. Okay? And because of this connection, if you have, for example, saturating activation functions there, okay, which will lead to vanishing gradients. This thing will be skipped, okay, or at least there will be another way for the gradients to move back through the architecture of the neural network. Okay. So you do that. You now just have a much deeper neural networks, but you add skip connections. Yeah, that's the same. And another nice property of that, of these skip connections, is that they will also smooth by quite a lot the landscape, the loss landscape. So they will also make the optimization of the neural network much simpler than if you had not added them. Okay. And so it continued like this for a few years. So you see in this histogram the performance of the winning solution for this ImageNet challenge. In 2010, 2011, the best solution, so this is before deep learning, the best solutions were given by shallow model, like regular machine learning models on handmade features. And you see with AlexNet, the community went from 25% accuracy, 25% error to 16% error. So in 1 year, just an improvement of 10%. And then all the next solutions, the winning solutions, were based on neural networks, with the common trend that the deeper, the better. And so we went from 8 layers, then to 19, 22, and finally 150. And you see that this correlates well with the error that you get. After, I think they run the challenge maybe for 1 or 2 more years, and after that, the best neural networks were doing better than human on the task. And so they decided to stop the challenge. Okay, so this is the first lesson you should remember. It's called deep learning because the deeper the better. Okay, but not only deep, you can also show that if you only increase the depth, eventually you will saturate. There are other things you can do to make the neural networks bigger. You can increase the width. So this is what you see there in the first plot on the left. If you increase the width, that increases the parameters, and that correlates well with the accuracy. This is another plot for the depth, and you see that the deeper, the better. And finally, also, this is something that maybe we don't think about often, but which is also important. The higher dimensional the input, the better. So the higher the resolution of the input, the better. At least in the case of images. Do you have questions? Okay. Then I want to conclude with a few comments on what's going on really inside these neural networks. So that's usually something that is a bit frustrating with deep learning, is that you will build this architecture which are more or less motivated, but then you instantiate to something very big with so many parameters, you train, and that works. But that's frustrating because you don't really know why it works. You don't really know, for example, why this neural network, this CNN, classify this image as an espresso or as a ladybug. Okay? And okay, in the case of vision, maybe we can try to interpret, but there are other tasks for which we don't have a good model. This neural network, they do perform very well, and maybe we could learn something about the task itself if we could understand how these neural networks are doing so well on this task. Okay, but that's unfortunately not something very easy with neural networks. It's very difficult to go inside and try to interpret why they perform so well. Still, there are a few things we can do. And specifically in the case of CNNs, we can look, for example, at the kernels. We can just visualize them as if they were images and try to see if they make sense. We can also look at internal activations in the case of images. So these slices that I was drawing there. We can also look at how the image is transformed and try to interpret what is being captured or used by the neural network to make its predictions. We can also look at distribution of activations. We can also look at derivative of the response. We can look at also, and this is interesting, at what we call maximum response samples. So one thing that we can do, I will explain that later. Okay, so let's take the first one, looking at kernels as if they were images. Okay, if you take, for example, this LeNet architecture, the one which was used in the video to classify these digits, and you have a bunch of kernels, and you look at them as if they were images, in this case 5 by 5 small images. This is the kind of thing of images that you would get. So how would you interpret that? What do you see? So for some of them, we could say, for example, for this one, it's detecting edges in some along some orientation. Maybe there it's looking for horizontal lines and maybe other things, or there diagonal lines in the other direction. Okay. But usually you see that, okay, it's not very satisfactory. If you look at the second layer and you look at all the kernels that you have there, okay, you get this gallery now of images, and good luck trying to interpret what's going on. If you look at another architecture like the AlexNet architecture, and you look, so these were these 11 by 11 kernels I was mentioning, and you look at the 21st of them. So what we call filters, by the way, is just synonymous with the kernel. You see this, in which there it's a bit easier to maybe interpret. You get, you have some kind of edge detector or compositions of several edges already in these bigger kernels. But again, it's not very satisfactory if really you want to make sense of what's going on inside the neural network. Another way, which I find quite interesting, is to look at what we call maximum response samples, which is to say, okay, you have, so imagine that this is part of a CNN, okay, X, and then it continues to produce some output. And then you say, okay, I will select some kernel, some neuron, some activation, some value inside the neural network. So I will pick some layer and some position within that layer. So this is what I call HLD. And then I will try to find the image X for which this value is the largest, for which this value activates the most. Okay, and how can I do that? But I can just frame that as an optimization problem, where I say I have a loss, which I will maximize, not minimize, where, for example, I look at the norm of some layer or some value inside this layer. Then I start at some random position, and then I do gradient descent on the pixels, not on parameters, on the pixels to maximize this activation. Okay? If you do that on VGG16, for the first layer of convolutions, these are the kinds of images that would maximize the activations of these neurons. What do you see? So VGG is a neural network trained on ImageNet on which you have 1,000 classes. You have boats, you have cats, you have dogs, you have buildings, many things. And I'm telling you, this is the first filters that are learned by the network. Do you see these boats, these dogs? What do you see? Yeah. Okay, you see texture, yeah. And what about this texture? Okay, Yeah? What else? Different colors. So of course, if you want to classify all these things, the color is very important. Yeah. You have different orientations. So here you have like horizontal lines, vertical lines, diagonal lines, which means that if you present this image and to the network and look at the activation of one specific neuron, if that specific neuron is about detecting horizontal lines, then of course, if you present an image full of horizontal lines, it will maximally activate. Okay, let's see then what happens when we go deeper inside the neural network. So this is for the second block of convolutions in VGG16. And these are the images that would make these neurons respond the most. What do you see? Well, we still have texture and some kind of lines. They are more maybe wiggly. And what's new is this. We have this kind of blobs that induce high activations inside the neural network. If we go deeper to the third block, we get something like this. What do you see? What do you observe? Yeah. Okay. Yeah. So now we get like there, it's some kind of mesh, some grid. And how do you think this mesh came to be? So certainly this kernel is looking at the composition of simpler kernels at the previous layer, maybe one for lines in this direction and the other in this direction. And so the two of them together will result in this kind of patterns. Okay? Maybe something which is not that obvious is that we see structure, or we see larger structure than before. Okay, we have larger lines, we have larger stripes than what we had there or there. Okay, this is related to the fact that as we go deeper and with this pooling mechanism, we are increasing the size of the receptive field. Fourth block, this is what we get. What do you see? Yeah. Yeah, okay, we see details now. What about the images themselves? Do you recognize anything or not really? These patterns, are they simpler or more complex than before? Yeah. And this is what you get in the fifth block. What do you see? Again, you get patterns that are now more elaborate, more complicated. Maybe you will start seeing things, for example, there. I don't know. It's up to you. But so this is what we can start trying to understand about neural networks. And everything that we see there is really a result of this composition mechanism. And really, the neural network appears to learn a hierarchical composition of patterns. So if we try to interpret the meaning of these layers, we would have that the first layers, they seem to encode basic features, such as direction and colors. Then these basic features in the next blocks, they are combined to form more complex patterns, like textures, or grids, or spots, as we've seen. And finally, these textures, they are further combined to create increasingly complicated patterns. Okay? And what is interesting is that never ever we encode ourselves these patterns. They are discovered by the neural network as we train it. Okay, so that's the best we can do really to explain these neural networks, what they do. There are, of course, many papers about the topic, but so far there is no in my opinion, convincing story about what these neural networks are really learning and why they are learning these things. But what is also interesting to notice, and I will conclude with that, is that because these neural networks, they work so well, these artificial neural networks, they work so well, they are also starting to become models of what actually happens in the brain. Okay, so we started with this inspiration from biology, okay, but there are still many things we don't understand in the next part of the brains. And one possible model is to say that the biological neurons are themselves organized in a way which is quite similar to deep neural networks and CNNs. And so this is a picture taken from a paper, and they have this quote, this sentence in the paper where they say, deep hierarchical neural networks are beginning to transform neuroscientists' ability to produce quantitatively accurate computational models of the sensory system. So meaning that you can instantiate an artificial neural network as a plausible model of the actual human brain. And these architectures, they manage to reproduce what is actually observed with experiments and measurements. And this is especially the case in higher cortical areas where neural response properties had previously been enigmatic. Okay, so this is a nice story because it goes back. It's not only biology or neuroscience inspiring deep learning. Now and more, it's deep learning inspiring what we don't know about the human brain. Okay, do you have questions? Okay, then before I let you go, I just want to do a quick recap just to go over everything we've seen. And because this is something I like to ask also during the exams. So let's say I'm giving you the task of building a neural network to classify dogs from images. Okay? Now you know how to do that. What would you do? What architecture would you use? Tell me. A CNN, okay. But in this CNN, if you had really to implement it, what would you use? What layers would you have? In which order? Yeah. Okay. How many of them would you chain? Okay, so let's draw the architecture. Okay, so we have the image. Then what? What do? You have you said a pooling layer, convolutional layer. Okay. Then okay, do you remember? That's too long ago. Yeah, and everyone can help, of course. Yeah, okay. So maybe a ReLU. Then okay, let's say pooling. Okay, maybe we repeat this thing, maybe 3 times. Then what do? We flatten, yeah. Then you said an MLP. Who said that? Yeah. And in the MLP, what do you have? You have layers, right? How many? Of what size? Yeah, but so you have to solve the task. What do you do? Okay, let's say these images, they are, I don't know, 400 by 400 pixels times 3 for the 3 channels. And we have, I don't know, 1,000 classes. So we are the MLP. What do we have? What do you do? There is no trick question. What do you have in an MLP? Yeah.
The first layer will be a linear layer with the size of the output of the pooling and the last pooling.
Okay, so linear.
And we do after the activation function,
Yeah.
and we repeat that basically the last layer should
What activation function would you use? Okay. Okay. Value. How many times do you repeat that? Okay, you have access to a supercomputer. So 1000? I don't know, I'm asking. Yeah. Maybe one. Yeah, I don't know. Maybe a few times. Let's say a few layers. Let's say 3. And then, so we have now a vector of size q, the width that we decide to have. Then, how do you design the output layer? So we have 1000. Okay, and how do you go from q? So this is a vector of size q to a vector of size 1000. A linear layer, thank you. So I will just say linear. Okay, and now we have a vector of size R1000. Can I use this vector as a vector of probability estimates? Yeah, softmax. Okay, and finally we'll get our predictions as a vector of probability estimates. Okay, in this block, we said convolution ReLU pooling, but we have not said how we configure these convolutional layers. What do I have to configure in a convolutional layer? Yeah. Yeah, how many would you have? Not one, please. Yeah. Okay, but we don't know that in advance. So what? 50? Of what size? So we have to specify the size of these kernel elements. No. So we have 50 kernels. Then we have to define the shape of these kernels. Okay. Why so small? Okay. This number, will you keep it to 50 as we repeat these blocks? What will you do? Why? Okay, good. Okay, so we have a network. How do we train it? Okay, and how do you do that? What gradient descent? We've seen 5 algorithms at least. I'm just telling you that because these are questions you will have to answer when you actually do the project, so it's good to talk about that together. So gradient descent, but which version? Adam, okay. What learning rate? Okay, that will be large, but you can try with that. Okay. So you would be using Adam, but on what loss function? No. And so for classification, what was the loss that we've derived? The cross-entropy loss. Okay? Please don't do mean squared error on classification problems. It could work, but yeah. How do you initialize the weights of this neural network? Okay. But interestingly, the first layer is a convolution. How do we initialize the weights of this convolutional layer? Okay, that's out of the scope, but usually we do something closer to Xavier initialization. So we use one of these schemes to initialize the weights. Then you start training. What do you do when you start training? Do you plot something? Do you monitor some quantity? Or you just hit the button and then wait? Okay. Okay, so let's say T is the number of updates, of gradient updates. And you see something like, actually on the mini batches, if you evaluate the loss on the mini batches, you will get something like this. When do you stop? Okay, so the validation loss, if you have a large validation set, okay, you could pay the price of evaluating it at every step, but that will slow down quite a lot your training. So usually you will also just look at a subset, and you get something like this. So when do you stop? So I can show you an actual neural network that we are training, and I'm not. Oh. Okay, we are looking at things like this, where these are two neural networks, and you have in red the training loss, and with the dashed line you have the validation loss. So when should we stop? How do you know that you are saturating if we can't measure it accurately and we only get to have noisy estimates? Yeah, okay. We can just also take averages of this thing, a running average that will smoothen the curve, and then make your decision based on that. However, what you observe is that your training loss is like this. It's not training, it's not learning. Okay, you plot the gradients. What do you mean you plot the gradients? What gradients? We have as many as we have parameters, so millions of them. Okay, and then you look at the norm of this gradient vector. Okay, so you will see it's close to 0. Yeah. So you go back to the architecture, you add skip connections. Where? This one? This one? This one? So there, like this? Before flattening? Just there. Okay, but that can't work because for a skip connection, you need to preserve the dimensions. Okay, but let's go back to this problem. This is what you see. Okay, you start training a neural network and it doesn't learn. What do you do? So we have initialized properly, we say Xavier initialization, we have reuse, we could add skip connections, and actually you may still have this problem. What are we missing? Okay, you could play with the learning rate, you would still get this. Okay, so you try another architecture. Okay, which one? Okay, it won't work, it won't help. What have we missed? So these are images. Each pixel is a value between 0 and 255. Ah, thank you. So we need to normalize the data. So to rescale the value, we could standardize the pixels, for example. Standardize. Okay, and now if you do that, and with everything we've done, you would get something like this. Okay? Now you reach some performance like this. Where is, let's say this is validation. But this is not good enough for you. Okay? I don't know, like the accuracy is only 70% and you think you can do better. What do you do? Okay, good. Yeah, so if you decrease, what could happen? Yeah, you would get maybe something like this. Anything else I'm missing? Yeah, that's it. Okay, so now you are good to go and you should be able to train your neural networks. Thank you.